We've been talking about kinetic energy in connection with flight of an airplane, and now I want to talk about kinetic energy generally. I'm going to kind of work backwards, become more and more general. Kinetic energy is that perception of energy that relates to movement. There are two kinds of energies, or two ways of looking at energy. One is in relation to movement, called kinetic energy, and the other is in relation to location, or separation between bodies, and that's called potential energy. But that does extend actually to compressing springs and so on. It's all to do with distance, and the definition of energy for potential energy is the force times the distance that the force is applied. Whereas kinetic energy is more concerned with velocity or the square velocity. And so I'm going to show you the equations and where they come from. So the equation we normally use is half the mass times the velocity squared. But Einstein refined this to c squared, the speed of light squared, times the observed mass minus the actual mass. Now I'm going to show you, although those two equations look so very different, they're actually the same if the velocity is small enough that it's not in any way competing with the speed of light. And I'll show you where that comes from later, but first I want to show you the similarity between these equations. The value of the observed mass of a body is, and I'll show you later where this comes from, is equal to the mass of the body when it's at rest divided by an expression that's known as the Lorentz transformation equation, and it's 1 minus the velocity squared divided by the square of the speed of light. And if the velocity is small, you can see that this is small and this becomes 0, so that the rest mass and the moving mass are the same. The difference is very small in what is moving, but you cannot ignore it, because if you ignore it and you say the velocity is so small that I can ignore it, especially when it's squared, then you get that the body is not moving at all. So you cannot say that the mass does not change for a body moving slowly. It does change, otherwise you cannot have these equations giving you the same answer for small movements. But I'll show you how you can approximate this without making v equal to 0, so that you can make this equation the same as this for slowly moving objects such as cars, even aeroplanes, and even spacecraft. Even 10, 20,000 miles an hour is small compared with 186,000 miles a second. And when you square that difference, you see this number is very small for anything that humans actually use to move. But when you're talking about particles, protons in the Hadron Collider and so on, they're moving near the speed of light, and this becomes very significant, and the mass increases several times in such a device. But that's for very small particles. So let's show how this can be abbreviated so that that's the same as that. There's what I remember from school was called the binomial theorem. I went to school 70 years ago, so my memory is not only imperfect, although it's pretty good for this subject, but also we learned things a little differently in those days. So the binomial theorem was one that said that you could, for example, if you were paying a small interest rate on a house mortgage, then you could say that you're approximately paying half the interest over a period of 30 years. And it's good enough for that kind of calculation. Just multiply the interest rate by the number of years and divide by 2, and you get that the actual interest you pay will be about 50%. I'm sorry, 50% of the rate that they quote per year. But that's what the application was there. But here it's the same thing. We can make v squared over c squared so small that we cannot ignore it, but we can at least approximate it. And we're going to do that in 2 steps. First of all, I'm going to take this square root. Square roots are not nice things, and nature doesn't like square roots. I think that Mother Nature doesn't have square roots in her mathematical skills, and in the same way that she doesn't have any fractions. She deals only in whole numbers of quanta of variables. But I think also she doesn't like square roots. So we're going to say, if you take the square root, which becomes what's called a series of expressions, you can say that, and I'll just take this out so that I can replace that the square root of 1 plus a very small amount, which is what v squared over c squared is. You can say that that is equal to, and you then expand this into a series, and you get 1 plus half of delta squared. This is, well, this is squared, I suppose. And then you get other expressions where the power is higher. And you can now say, and this is the binomial theorem says, if you make the power higher, a fraction becomes so small that you can say it's 0, and it's okay to do so. And here we're not making the square equal to 0, we're making the square, we're using that square because that's not small enough to be 0. It's very small, but if you ignore it, you're going to end up saying the body's not moving at all if it's moving slowly. So, but we can ignore the next expressions, which I believe is to the 4th, I'm not really sure. But anyway, that is certainly smaller by another level, and so we'll ignore that. So you can say that, and now you see we've simplified that equation. Now there's another way you can abbreviate it. And did I have a minus in here? I think I did. Yes, I did. I had a minus in it. Oh, no, that's right, I had a minus. But that's underneath the equation. So we had here that m naught equals m, and we had that underneath. And we're going to say that that is okay to say that it's equal to the small amount, small percentage or small fraction squared. Now you can approximate that in another way. You can say that is the same as m plus 1 or m to the 1 minus delta squared over 2. That's correct. And so now we can say that we can now substitute that in there, and we can say that this equals c squared into m into 1 plus m plus, I've got this the wrong way around, I think, somehow. It comes out to 1 plus delta squared over 2 minus 1. I've got that wrong way around somehow. I forget how I did that. You'll have to go back and do it for me. I'm not going to do it again. But I can assure you it's correct. It comes out to that, and that is equal to half of m delta squared, which in this case is half mv squared. So by approximating this as being a very small change from that, you can halve it, which is like the binomial theorem would halve the interest, so we can do the same thing here. And so this equation is not as far as it looks from the standard equation for kinetic energy, but it's and so you can approach. It's not really totally different. When the velocity gets much higher for v, then of course you do have to calculate the amount fully, and you do that by using the Lorentz transformation, as I said. So that's just to point out that this is not that much of a change for most of us most of the time. Einstein's contribution was more important when you're talking about particle physics and astrophysics, where you get very high velocities and over a long period of time those velocities become important if you have to consider the energy as being increasing the mass of something. For example, it's related to why the moon has a circular orbit, is because the moon, although it's traveling fairly slowly now, at about 2,000 miles an hour, just over that, as it orbits the Earth, originally it was traveling much faster than that, about 10 times faster, and over billions of years, that small difference in mass has the effect of changing the moon's velocity orbit, which was originally a very narrow ellipse, almost missing the Earth every time it came by when it was first in orbit, has now become circular over billions of years. And so you cannot ignore this for astronomy over long periods of time, just as you cannot ignore it for particles. So at least we've got to the point where we understand that this equation is all right, is not made void by Einstein's special theory of relativity. But now, or rather perhaps in the next video, because I must be getting near to my 15-minute arbitrary limit that I've set, this is all right, but there's a problem with it still. And that is, as I mentioned in my previous videos, that there's only the mass of a moving body. And the mass of a body it's in relation to, for example, an airplane flies relative to the Earth, the moon orbits relative to the Earth orbits relative to the sun, and so on. You cannot ignore the mass of the Earth, because that is associated with the kinetic energy, although it's not in the equation. And as I pointed out before, it's in there indirectly because the velocity of a body orbiting the Earth depends on the mass of the Earth. And a body flying in an aeroplane is not orbiting, but its gravitational attraction to the Earth depends on the mass of the Earth. And if that were greater, if the Earth had a greater mass, the plane would have to fly faster in order to stay up there. So it is in there, but I don't like the fact that it's not in. It's not the mass. There's not there, and I think that we should have two masses in there. And that's I will say this before I end this video, and that is that when you look at potential energy, this does have both. And using Newton's equation for force, potential energy is equal to the mass of one body times the mass of another body times the universal gravity constant times the difference between the reciprocals of the two distances is over which you're measuring the potential energy. This is potential energy between, say, between the ground and something. If I were to throw up this, what might be here, when that leaves my hand, it goes up and it gains potential energy. That it also has kinetic energy. And when you compare these, you see this has two masses, this does not. So how could this be the same energy or the same kind of energy as that? And the G actually is part of the secret there. But now we're talking about potential energy. I'll do that in the next video. The G has a mass in its denominator which cancels out the Earth's mass, or appears to. But that's it. So you see, our perception of energy is kind of mixed up in that we don't know whether isn't clear whether it's between two bodies or whether a body moving can have kinetic energy. without it being, without considering the mass of the body in relation to which it's moving. So that's enough for this video. We'll go into a potential energy later and say some more about kinetic energy. And I'm going to come up with a proposal to make these equations much more similar. So thank you for watching this.